Well, hello everyone. I'm the boring old git, and this is the first of my wastes of money, brains and time. It's a Hewlett-Packard 4957A, which was on eBay as faulty. I didn't realise just how faulty it was when I saw the advert. I suppose I should have guessed, because it's missing the bag off the top and all the cables. But I've been watching the videos on YouTube, and all it was going to be a capacitor in the power supply. Yes, I'm looking at you, all the various fixes out there, and it's always a capacitor in the power supply. The unit itself looks fairly clean. It's got various serial ports on the back, and it just needs a little bit of repair work, though I didn't realise just how much repair work it actually needed when I started looking at it. So the first thing to do is open it up. Check the fuse. The fuse was good, so this made me feel optimistic that nothing too catastrophic had happened. How wrong can you be? One thing I noted with this, you'll see me putting a small S there, one of the screws is shorter than the other, so this was to make sure that they all went in the right place. Getting the top off was a little bit awkward because of the floppy disk catching up, but there it is open, and initially I couldn't see anything much the matter with it. It's a mix of technologies, but nothing was too obviously bad until I started looking at the I/O board, which, as we'll see, is not in a happy state. So here's the serial input board. Was about to take it out, and I just noticed the battery was wobbling. It has restraints at the back which had broken. So pulling out the serial input board, I don't think the IC is supposed to be missing its top like that. Plus, I don't think that the resistor pack should be burnt like that, and also it looks like there's a melted track. To make sure I knew what state things were in, I measured the resistance of all the power supplies to ground. What I found was that the two plus 12 volt lines and the minus 12 volt lines were shorted to ground. This was when the serial input board was plugged into the main board. If I removed the serial input board, then what I found was that the 5 volt rails seemed good, and the plus or minus 12 volt rails, the short was removed. So it looks like a lot of the damage is on that input board. Though I did find later on that there was an awful lot of damage elsewhere in the system. Pretty much everything on the plus 12 volt lines were affected, and large chunks of them had to be replaced. So this is what I found when I took the front off the input board. This was damage that wasn't visible while the panel was on. So we've seen this before with the burnt track, the burnt resistor pack and the burnt IC, but this is what was underneath the metal plate covering up the board. The IC there, I did actually manage to get a number off it. It's just an ordinary dual comparator, but it's clearly taken one heck of a hit. That pin in the lower left corner, the blob there isn't solder, it's actually the pin itself melted. So this is the input circuit for the analyzer. What you've got is this section here is the input sockets with the switches and the jumpers, so you can reconfigure the input as you need. You've got a set of protection diodes to protect the input against overvoltage, a series resistor to protect from overcurrent. Then this circuit here is a little helper circuit. You can feed in from jumpers onto this pin, and it'll tell you whether it's at mark space or whether it's floating or at ground. So the components that were damaged or destroyed are that one there, both of those which are actually the pair of resistor networks, and then this comparator here. Everything else was absolutely fine, so it looks like what's happened is that this has been connected up and to something with excessive voltage, and you've had fault current flow through here, which has blown that resistor, and probably something on the analyzer board. It's gone through these protection diodes, destroying them, through that diode, destroying it, and then it's come in on the 12 volt rail through into this, and I think this is what has taken the bulk of the energy. But clearly things have also got through onto the main board and caused some damage there. So I've got all the failed components out of the input board, looking at it just to see if it's repairable. I think it is. I think we can fix this up and get it working. The big question now is there any value in trying to fix the rest of the system, or is that just too broken to be worthwhile? So the first stage in seeing if it's worth repairing is to power it up just on the 5 volts. If you heard the beeps, then yes, it had reset and there was indications on the front panel, though not totally correct. So now I'm plugging in the scan coils and going to power it up with all rails to see if we get a raster. And we've got something on the screen, but clearly the vertical scanning isn't working. So, and plugging in a coax cable into the back, and we'll use that to see if we can get any sensible composite video out of the system. Looking at the output on the back, it looks like we've got a good video signal there. There's horizontal and vertical sync and what looks like sensible video data. So we'll hook it up to a monitor and see what we see. I did take a quick look at the drive to the vertical scan coils, and this is what I got. There's a little bit of something there, but rather than less than a volt of swing, I would have expected something much closer to 10 volts. Apologies for the use of shaky cam on this section. I was using a monitor sat under my desk. You can see we're getting sensible video coming up. The buttons are responding and the thing seems to be behaving correctly. It looks like the system is largely functional. I do keep noticing that the software version is A0001, which from Curious Mark's video indicates that it hasn't got the 80 column mode enabled. I did find the self-test, so we're running the self-test operation here, and as you'll see as it runs through, everything is passing apart from DLC, which is the data link controller. So it looks like it's worth taking the next step and seeing if we can fix the power supply and main board. minus 12 volt regulator was blown. The plus 12 volt regulator is blown. The diodes for the plus 12 volt regulator were blown. The diodes for the plus 5 volt regulated line were leaky, and the diode for the minus 12 volt line, while it still appeared to be functional, was very burnt. The reason you could power the unit up, it was in the undervoltage lockout condition, so it wouldn't power up, which was due to this capacitor being faulty, which is the same fault that Curious Mark had on his unit. So you do have to change C7 if you're servicing one of those things. So I'd taken out that one, that one, that one, and that one. And I checked the feedback circuits and they appeared to work. I replaced that capacitor and powered it up, and it did come out of undervoltage lockout, but the consequence of that, I think, because I'd forgotten to put the 5 volt diode back in, was that the main drive transistor and its inline fusible resistor both blew, taking out the main fuse. Having decided to replace the power supply, I chose a Meanwell RPT60B, which is a popular supply for upgrading the Amiga. It's close in specification to the Yokogawa supply that was fitted, but much smaller, so I needed to 3D print a mounting plate for it. This positions the new power supply at the same level as the old one, just to make sure that we don't have any problems with clearance when the thing's put back together, because the power supply sits around the same area as the CRT. I also had to provide a new earth connection onto the power supply because it doesn't have a connection on the mains connector, and I wanted to leave that as unchanged as possible to give the option of going back to the older power supply at some point in the future. I had to fit a new earth connection, which wasn't provided before, to earth the enclosure for the floppy disk drive. This is because it's got a mounting post which goes to a screw on the top of the case. So if you got a fault within the unit, that screw could potentially become live. With the original power supply, this was managed by connections on the actual PCB. But of course, with the 3D printed adapter, that connection wasn't there. I initially used a ring terminal screwed onto the top, but this caused a problem in that it was only contacting the plate through the threads of the screw, and I couldn't get a good connection. Because the ring wouldn't fit under the moulded bit of the mounting, I converted it into a fork connector, and that then just nicely slid onto the plate and could be clamped down onto it, giving a good earth for the enclosure. The last part of the process was to connect the DC rails from the output of the power supply onto the cable for the main board. This is because the layout was in a different order, so I used the voltmeter just to verify that everything was in the correct position before we plugged it onto the main board and risked damaging anything. One unusual aspect of the design is that the power supply supervisory IC was on the power supply board, not on the main board. This means that the system reset is generated on the power supply board. This function's not available on the replacement power supply, and I did find that without it I couldn't get the system to reliably start on power up. I've mocked up just a simple reset circuit that gives about a 500 millisecond delay holding the thing in reset on power up, and that seems to be more than enough to guarantee that the system resets perfectly every time. So first up on the main board is fixing the vertical scan. I've run some tests on it which were a bit boring to put up on a video, but we know that the FPGA is good because we've seen the composite video, which means that all these components around here are good because they're generating the composite video. We've got a -5 and a +5 regulator. These generate the rails for the scan coil, and they're good. The gaps there are the drive transistors that actually go onto the coils themselves. These are out because I was checking them on my component tester. Those are also good. So that really leaves only one candidate for replacement, and that is the quad op amp that drives the transistors. Hardly surprisingly, this is about the only component that's on the +12 volt rail apart from that regulator. So after a short wait for a well-known international auction site to do its thing, in goes the replacement chip, ready for testing when we've done the rest. So without any schematics or service information, all we can do now is play Hunt the Thimble. So after tracing through, I found that the input board feeds directly to the highlighted chips, the 3 LTC 1032s, which are all RS232 drivers fed by TTL inputs. These chips are used in the simulation mode when the analyzer is able to drive the serial connection. When I powered the unit up, the devices were running extremely hot to the touch. So it was back to everybody's favourite international auction site to order replacement chips, which took a couple of weeks from China. So I broke out the hot air gun to start taking the chips off. It's at this point I learnt just how fragile the PCB is, and when I took the first device off, unfortunately it brought 4 of the pads with it. 2 of them are no connects anyway, so that's not a problem. But it did disconnect the ground pin, and it did lift 2 of the signal tracers. I managed to rescue the 2 connections, though I have noted where they go in case they fail in the future, but the ground will need a mod wire. So while I was waiting for the parts to come from China, I was trying to mop up a couple of problems I'd seen on the board. First of all, ready to send and carrier detect seemed to be shorted together. I could find no sensible reason why that would be, so I tried driving about an amp through the shorted lines to see if I could either blow it open or at least see where it was getting hot. In either case, I couldn't get a result. It just seemed to sit there at about an amp, and I couldn't find for the life of me what was getting hot. So I decided to shift focus onto the data terminal ready line, which appeared to be shorted to ground. So again, hooked up onto the line. It was reading about 10 ohms to ground, so I tried again to find out where the short was and what was getting hot. And as the current came up, it suddenly surged and then dropped down, and the magic smoke came out. So there's the culprit, that little diode there. All the magic smoke came from that. Turns out that the protection network on the input board is repeated on the main board and connected to the same lines. The only difference is that this set are going up to the V35 interface on the rear panel, not to the RS232, but they're in parallel with the protection circuits on the input board. They use the same drivers and input chips, and clearly these were taken out at the same time. So, breaking out the hate gun again, it's time to remove these. I don't actually need these protection diodes. There's protection on the input board, and I'm not likely to ever use the V35 interface. So we're on the home straight now. This is bringing the unit up with the repairs done, but without the drivers in. That'll be the next stage. And I'm just checking here to see if all the inputs are responding correctly to both mark and space. It's obvious to say it, but the repair to the vertical scanning circuit has clearly worked because we're getting a proper image on the screen. So the last part of the repair to the main board was to solder in the new driver ICs, which you can see in the photograph, but this did throw up one last problem. It turns out that there was damage to the FPGA that manages the data link controller. It was no longer able to drive the control line on the DCE simulation section of the board. So what I've done is put in a switch to allow that option to be enabled or disabled. It's a manual process, but it's less risk to the board than actually desoldering the FPGA and putting in a new one, in my opinion. I've also replaced the batteries for the backup. Given the price of the quarter-size AA's, I actually went and bought full-size AA batteries because they were about a quarter of the price. So I've just made up a little assembly and fastened it to the bottom of the floppy disk housing. Once I'd fixed the main board, that wasn't the end of the repairs. The floppy disk drive had also been damaged when the system was blown up, so I decided to replace it with a Gotek board. I chose the HXC 2001 firmware because it gives a lot of configuration which I needed because of the non-standard disk format. This meant I had to design a special housing in Fusion 360 to 3D print because there is only 7mm available at the front of the unit when the keyboard's closed. This meant I couldn't use any of the standard housings if I wanted to use the rotary encoder, so I produced a special housing designed to fit the space, along with a little slot to actually store the memory stick in, so everything could go with the instrument. The housing printed well and everything seemed to fit in it okay, though some of the tolerances are a little bit tight and I didn't really need to use the brass threaded bushes. I could have just threaded the M3 bolts straight into the plastic. Maybe I'll do that if I ever build another one of these. But it all fitted together, the knob worked okay and everything was accessible. The next problem was the data cable connecting the floppy drive to the main processor. Rather than having a separate power lead as in a PC, the power connections are taken up the ribbon cable. This isn't supported by the Gotek board, which uses a standard interface, and if you don't modify the cable, you end up shorting +5 to +12 and ground. So from the manual for the floppy drive, cores 3, 5, 7, 9 and 11 are plus 5 volts, and cores 29, 31 and 33 are plus 12 volts. Those need breaking out of the cable and bringing through to a connector that can go on to the power connection. You don't actually have to bring the ground across, because obviously that goes up in the ribbon cable. So to do this, I slit out the cores only by about a centimetre. Then I soldered them up onto flying leads and mounted up a connector which could then fasten into the power connection on the GoTech. So this is it, ready to go back into the machine. Initially, I used the green LED that was provided on the GoTech board, and then a second LED which I hooked onto the bright gate signal so I could see when the unit was being accessed and when it was being written. However, it turns out that with the HXC firmware, the access LED is actually linked to the drive select line, which is always enabled on the 4957. So what I did was I've taken that out of the way, and I've used the motor on signal to indicate that the drive is in use, and then the right gate to indicate that it's doing a right operation. So the first thing is to rerun the self-tests now everything's together. I'm running the loop test in RS232 mode just to see what happens. The important thing is to watch the number of errors and the loop count at the top. Here's the indicator lights as they change state as it does the DLC test. And coming back, we're at loop 4, loop 5, no errors reported, so I think we can safely say that the machine is working. The next stage is to try actually sending data out and returning it. So what I've done is I've put a loop back on DTE and DCE, and I'm setting it up in terminal mode with the local echo off, so it'll only display what is sent back. Initially I've set it up at 19200 baud, and here we go, typing away on the screen. It's being sent out on the serial port, and then it'll loop back and be displayed on the screen. If that connection wasn't there, then you'd get nothing on the screen. If I'd turned the local echo on, then you'd get double characters on the screen, but this is the clearest way of doing it. Going back now and resetting it into 300 baud, so really slow. You should see it's still responding, but the flashes on the lights are much slower because of the reduced baud rate. Again, everything seems to be working, so I would say we're good to go. So the next thing is verifying the performance of the floppy drive. Initially just pulling up the directory of the file I've got in there. It's got a couple of things on it. Pulling the disk out, you can see that it goes to disk out when you try and access anything. Reinserting it, I had to reselect the HFE file, which is the disk image. But once I did that, it would then read successfully. The next part of the test is to copy the disk onto itself. So to do that, it has an application which copies the disk into memory and then copies it back. The big problem I had with setting up the floppy disk is that Hewlett-Packard have multiple formats for the 720K floppies. For instance, the 9845 uses 9 512 byte sectors per track. The 4957 uses 16 tracks of 256 bytes. I ended up actually having to handcraft a disk image. I couldn't use the format utility, that just seems to crash the system, and I've seen notes online that it doesn't work. So what you need is effectively an image of a blank formatted disk. I have produced one of those, so I'll link it in the comments, the image and the configuration file to use with HXC to get the correct configuration of the I/O to do disk insertion and removal detection. Everything is now working on the instrument. It now appears to be usable, and hopefully it'll appear if there are future videos that need it. All that's left to say now is thank you everyone for watching, and please don't forget to like and subscribe, then you'll get notified if I make more videos. Press the button if you want to be notified. If you do decide to dislike, please leave a comment telling me why, and then I can improve what I do and maybe make it to your liking next time. Thank you. Bye.